Welcome back, everyone. It's been quite long these 2 days, but this will be our last talk. And after that, we'll have a closing remarks, and then there'll be a wind down session under the session tab so people can turn on the camera and chat and get to know each other a little bit more. So I'm going to bring on Kai, who is going to be telling us about mathematics for developers. And of course, if you have questions, go ahead and put that in Slack, and we'll be answering them after the talk and also just afterwards in Slack. All right, take it away.
Thank you. Good afternoon to everyone, and good morning from a very nice sunny day in Wellington in New Zealand. So I'm going to spend like about 30 minutes talking about mathematics, and specifically mathematics for developers. And before, when you go back like 20 to 30 years, the typical path to a software development career would have been a degree in computer science or mathematics or something that is closely related to either. But I think over the years, our ecosystem has changed quite a lot. And a lot of developers have joined the industry from all sorts of walks of life, self-educated, developer bootcamps, cross-training from other professions, etc. And mathematics is not necessarily a requirement to be a good software developer, but there are quite a lot of areas in our day-to-day work that use mathematics to a varying degree, right? Like think about stuff like animations, machine learning, functional programming, or lambda calculus, or even, more specific computer science topics. So this talk is not specifically about mobile or Android. We're not going to use any libraries, or I'm not going to explain any libraries. But the idea is to give you a level of inspiration to get into mathematics, if you're interested and if you're inclined to do so. So my personal history, how I got into this topic of math is I'm a software engineer, right? And I grew up in Germany, went through the high school system there, and attended uni there. And then at some point moved to Wellington here in New Zealand, where I'm currently living. And the German high school system is essentially 13 years. And the last 2 or 3 years, you have to choose some majors. And I went with math and physics. And math in high school is pretty much like applied mathematics. You would calculate things, right? You would calculate, the size of a triangle or the size of a certain circle and stuff like that. And then because I enjoyed that, I went to uni, started my math degree, and all of a sudden, everything was very different because you have to prove everything, right? And it's not that much about applying mathematics anymore. It's about the fundamentals and building up the concept behind mathematics that you would then occasionally use. And I finished the degree, started to work as a software engineer in web development mainly, and I didn't use my degree much until the whole trend of machine learning and AI all of a sudden popped up. And I got interested in that and did the original Coursera MOOC about machine learning a while ago. And I realized how much mathematics is involved in machine learning and in AI and in dealing with data. And funny enough, at the same time, I also realized I didn't find it hard because I had that background of like a university degree in math that makes it kind of easy to juggle with massive equations or systems of equations. And a lot of my friends who didn't go through this formal math education struggled quite a lot with that. I mean, they found other bits in this or similar courses very easy, but struggled specifically with the formalisms around the math. So it made me realize that a lot of people didn't have that easy access to the formal aspects of mathematics. But why would you even care as a developer, right? Because you build software, more or less. And I think there are a few good reasons why you would want to be interested in mathematics. For a start, it's a really nice tool that improves your abstract problem-solving skills. And that's one of the things, funny enough, that I took kind of for granted, even things like how do you approach debugging a problem in your code. But I think my university training in mathematics helped me a lot to approach problems in a very structured way. And that's a nice skill and a nice ability to have in the first place. Then you can also use it in your day-to-day development work, right? So for stuff like animations and transitions, logic, machine learning, dealing with data, or just dealing with, economical or scientific business problems, or understanding, for example, exponential growth in our current global health situation, things like that. It's all mathematics behind that. And the third big reason is fun, right? Like look at like this beautiful little fractal, which is essentially a complex function. And if you're old enough, you can remember back in the day when calculating one of these images took, the best part of a day on your computer. What I personally do is I have a math calendar. So I've got a calendar for the whole year, and each day has a math challenge. And sometimes, you can do it in a minute, and sometimes it takes me, 10 minutes or half an hour to do one, because they vary quite a lot in difficulty. But it's a really fun, nice thing to do outside of your day-to-day grind of writing code. Let's have a quick look at this. This is the map of mathematics. And it's made by a person called Dominic Velliman. He's got a YouTube channel called The Domain of Science, which is really good. And I've got the link to this YouTube channel on one of the last slides with the resources. But he actually went through the effort of mapping different fields of mathematics, right? And pretty much you start with things like the origins, which is this gray, brownish area in the middle. And that has a lot of the basics, right? Like what is a number? What is, basic geometry, et cetera, et cetera. And then you extend out to other areas like number systems and structures and calculus and applied mathematics like statistics and probability theory, et cetera. That poster, or this graphic can be bought as a poster. I'm not making any money off that, but it's a really, really beautiful poster if you're into these kind of things. So have a look at that. The traditional way of getting into mathematics is usually through traditional schooling. And I totally acknowledge that not everyone might have access to that, or not everyone goes through exactly the same experience, right? But typically, you have primary school, let's say 4 to 6 years, depending on the country you grew up in, and you would learn counting and numbers, and you would learn basic addition and subtraction, multiplication, division, and some basic geometry, and maybe you deal with sets and like intersection of sets and stuff like that. And then you have high school, and that might take you from something like year 5 to year 10 in kind of a middle school setup, and you do arithmetic with larger numbers, you look at different number systems, you learn about equations, and you do more geometry, and you might learn about probabilities like rolling a die and stuff like that. And then in the last years of high school, let's say your 2 to 3 last years before you would go to university, you normally get into calculus, linear algebra, and some more geometry, and you do a proper course on statistics and probability. And that's, a very high level overview. But that's usually what I find when I talk to my friends who went through this traditional schooling. So calculus, let's start with that. It's kind of the field of functions, where you look at a function, the rate of change in processes, limits, and convergence. And typical things you would do there is you have to find a derivative of a function, you have to find a peak of a curve or a trough of a curve. And usually at high school level, this would be a function that maps from real numbers into other real numbers. And if you find this graph familiar, that's usually what you do, right? You have the green line is kind of a curve, and the purple line is a secant, and you use that to approximate the incline of a function. Very typical high school math, what we see here. Then linear algebra. That's the other big section that you usually go through in high school, which is dealing with vectors, matrices, and what's called algebraic geometry. So again, this kind of, visual might look familiar. You have some sort of a coordinate system, and you have arrows representing vectors. And a vector might, in physics, be a movement. It might be a force. It's just a nice way to, display these kind of things. And with vectors, you can do math. Here we see a vector addition, and we'll get back to vectors in a few minutes. And the third big topic is usually statistics and probability. And that is looking into chances of things happening. Like you roll a die, typical 6-sided die, what's the probability of getting a 6? Or you look into stuff like trends, into distributions of data. Here we see like a Gaussian normal distribution, which is also known as the bell curve, in a variety of different flavors, shifted to the left and to the right, and with different kind of peaks and troughs. And all these things are usually assumed you would know when you come into high school, for better or worse, right? I'm not saying this is a correct assumption, but that's kind of what university teachers expect you to know the basics of. If you have kind of forgotten a lot of that high school education, or if you never had it, or maybe, in high school you didn't see the need of learning about probability or statistics, how can you now get back into it? And the general approach that I find works really well is try to pick a goal, like a practical goal, and unpack it. And with unpacking it, I mean work it backwards. So for example, if your goal is you want to understand how animation works and how to rotate something in a 2D or 3D environment, you do some research and you find the topics you need to deal with here are vectors and matrices and trigonometry functions. And now you have that big question mark in front of your head, and it's like, how do I even get there? And what does it even mean in the first place? So you do some more research, and you find a definition for rotation, for example, and it says the turning of an object or coordinate by an angle around a fixed point. Rotations can be implemented using rotation matrices. Interesting, cool. Let's have a think about what a rotation matrix is and what vectors and matrices are in general. This graph shows a system of coordinates. We have like a 0, 0 point, which is also labeled with A. We have a point B, we have a point C, and a point D. And between A and B and C and D, I drew a vector. Right? Like that is representing a vector in a two-dimensional plane in this case. And because the vector AB ends up in point B and starts in 0, 0, the definition of that vector from a mathematical point of view is 5 and 6. And it means you go 5 units towards the x-axis, and then you go 6 units towards the y-axis. And that's represented in that vector. You go to the right, and then you go up. The vector from C to D is slightly different. So we're not starting in the origin of the coordinate system. We start in a more or less random point. And the description of this vector is 5 minus 1, because we're moving 5 to the right and minus 1 to the top, which basically means we're moving down 1, right? And you can see this movement reflected in the difference between the points C and D. You'll find D as 5 to the right and 1 unit further down than C. The interesting thing is, with these vectors, we can now actually use them to apply a rotation to one of them. The rotation matrix we want to use is the one in the upper left corner, 0, minus 1, and 1 and 0. And how this works, I'll jump to the next slide, is basically you take your rotation matrix and you multiply it with the vector you want to rotate. So I'm basically saying my rotation matrix 0, minus 1, 1, 0 gets multiplied to the vector of 5 and 6. And you would have to look up how matrix multiplication works. But the outcome is we get a new vector that is -6 and 5, which is the vector from A to E on this slide. And the interesting thing is, when you look at it like visually now, you can see my original vector from A to B has been rotated exactly 90 degrees to the left, in this case, anti-clockwise. And that's kind of cool because it means I have a rotation matrix, or I have a formal system which I can use to rotate anything into these spaces now. So where's this rotation matrix coming from? This rotation matrix specifically was only a one-off use case. It's 90 degrees counterclockwise, but it illustrates the idea, right? If we look at more generically what a rotation matrix is, we'll find there's a more complex definition. So that matrix is using functions like cosine and sine, and we have a more complex matrix. If we have a certain angle being given, we want to rotate around, we have to do cosine from phi minus sine from phi, and cosine from phi. So the matrix becomes more complex. Next step in your investigation would now to think about, like, what are these functions? What does, sine and cosine even mean? And that takes you into trigonometry functions. And trigonometry functions essentially create a hook between geometry and calculus. They're kind of a translator between two very different worlds, right? And in physics, these kind of like functions are called periodic functions because they don't have an end, they repeat, and they kind of simulate a periodic physical event. For example, sound is usually expressed by this, like a waveform, more or less. But these functions are very helpful to map between angles, like you want to rotate something by, I don't know, 60 degrees, and the world of calculus and linear algebra, where you apply these kind of visualizations or rotations to objects you're dealing with. But at the end of the day, this opens up more questions, right? Like, so the next question would be, what is a function in the first place, if you have no idea what it is? And again, what are sine and cosine, and how are they defined? It can be tricky to unpack all these things, but we'll get to that in a few minutes and talk about it a bit more. Another example I wanted to show will be also something visual. We get to that in a few minutes as well. But let's have a quick look at the topics, again, that we investigated for our rotation example. So we have vectors and matrices, and we have trigonometry functions. And obviously, like 30 minutes is not enough to explain all these topics so that you can actually start working with them. But what your next step in your research would now be is to unpack your topics and then look at the details of these topics. So for example, when I do that, I find that matrices in 2 and 3D, or dealing with them, requires knowing linear equations and a Gauss algorithm and notations. And if I want to deal with vectors and their geometric representation, I need to know something about vector arithmetic. And I need to know some geometry basics. And I need to know some algebra basics, like equations and how to solve them. And I actually need to know some calculus, like some basics about functions. And that can be a lot. Don't get me wrong. That is not trivial to learn all these things. But you have to unpack and break down the things you need to know to get to your actual destination, which is understanding how a rotation works. And obviously, there is a point where you have to do a cutoff, where you have to say, I don't need to prove all these things formally. It's enough if I know how they work, right? So another example is another visual one, right? Like, think about visual animation. And we want to move an object on the screen. That might be a website or an app or something like that, whatever you're working with. And we want to deal with the typical easing in and out scenario. You have an object that is maybe static, and you want to accelerate it, move it somewhere, and then slow it down and have it static at a different point. And this is kind of controlled with easing functions. So if you want to understand how that works, the things you need to understand are vectors and matrices again, functions and calculus, and you need to know a little bit about physics and how physics work. And I'll show you some videos that I took, some recordings. The first one shows moving, or all of them will show actually moving little boxes. And you can see in the top example, it's a very different kind of acceleration from the bottom example. And they are defined by the function, by the curve that is shown right above the animation. The first one is kind of to the power of 2, and the second one is to the power of 5. So you see like the acceleration kicks in much more rapidly all of a sudden towards the end. The next example, similar, but now we're having a bit of a bounce back effect. So it's pretty much you're pulling something back and then you let it go. And you see the curve above it. And the function, again, is a mathematical expression of that. And in this one here, we see like a proper bounce effect. And again, you see the function above that is kind of interesting. It's not trivial to describe because it contains stuff to the power of 2 and a cosine and pi and a few other things, right? But all these easing out and easing in elements can be described by mathematical functions and calculus. So looking at what we would need to know to do this or to deal with this topic properly, matrices in 2D, that's cool. We have looked at matrices before. We need to know some things about vectors. We need to know some more things about calculus and basics of physics and physical mathematics, potentially, and also some numerical mathematics if you want to simulate these kind of things. But what happens is when you now compare that, what you looked at, to what you looked at in the topic before when we talked about rotation, it pretty much means like there is a lot of stuff that is overlapping, right? So, you know, matrices, vectors, and calculus, or elements of calculus, were part of the necessary knowledge and topics to look at when dealing with rotation as well. Another example, you want to get into data analysis or AI and machine learning. So the typical topics that pop up when you look into that are massive matrices, like huge matrices, algebra to solve equations, and statistics and probability. And breaking that down, we'll find we have matrices, but not in 2 or 3D spaces, because it's not really something we look at, but in an n-dimensional space, because those systems can become really huge. And there might be, you know, a whole new category of matrices in there that are called sparsely populated matrices, where nearly everything is like 0, and you have a few fields or a few elements of data that you're actually looking at. Then we need to look at algebra. We probably need to know something about probability theory, and we need to know something about statistics. But again, comparing it to the broken down topics that we already looked at, you find that some of that stuff happens or is necessary in other elements of math again, right, as well. Algebra was a topic in both rotation and animation. Matrices, maybe not in n-dimensional form, but some of the knowledge you would have gained through, you know, looking at rotation or animating things is useful here, actually. And if you take this through all these kind of problems that are relevant and interesting from a software development point of view, you pretty much find that math acts like Lego. It gives you a set of building blocks that you need to arrange in certain ways to get the outcome that you want. Going back to that map of mathematics from the beginning, the yellow bits I marked on this map are pretty much what we looked at. And you can see how they arrange really closely around the origins of mathematics. So what you need to know for a lot of the things that are relevant as developers, you don't need to go to, the last corner of this map of mathematics. You can actually achieve that by not straying too far from the actual origins, which is really cool, right? I mean, sure, if you are interested in things like complex analysis and fractal geometry and stuff like the butterfly effect or gaming theory and stuff like that, you can find that on here. No doubt about that. But then you are looking into very specific interests already, right? But for a lot of relevant things, the learning path is not going to be extremely long and complicated. So now to close, let's have a look at how to get there. So what are some practical ways of learning and good resources that might help you to get started? The ways of learning are different for everyone. I strongly believe in that. It's kind of hard to give you one correct way of how to learn mathematics. For some people, video lectures work really well. That might be uni school style or MOOC-based on a certain topic, for example. For other people, interactive workbooks are really helpful, where you have maybe apps or websites that interactively talk you through things, where you have to try out stuff yourself, like the animations, for example, that I showed, or you rotate things, or you play with matrices interactively, stuff like that. So that can help you if that's kind of the way how you learn. There's obviously lots of reading material out there. So there are some good websites. Traditionally, mathematics is a field in which a lot of knowledge is taught in books. And that is an issue of accessibility in a way that a lot of people don't like to read books about formal math. But it's kind of founded in the history of the subject and the way how it's always been taught, right? And we have slide decks from university lectures, for example, or slide decks of talks people gave on interesting little problems like how to calculate prime numbers. So lots of stuff is out there as well. And then there's a bunch of apps and other software that is useful if you want to get back into mathematics. Let's have a look at some lectures and MOOCs. So one that is really good if you need to get started with the basics is Khan Academy. They usually go from primary school to pretty much uni prep on a skill level. I know a lot of people who like Khan Academy. I also know a lot of people who didn't like it. So my recommendation would be give it a try and see if that kind of style of learning is your thing. Then there is the YouTube channel of Dominic Velleman that I mentioned before, who's the creator of that map of mathematics. It's called Domain of Science. So he has a few other things on there as well, but he has a lot of really good YouTube videos on mathematics or certain topics in math specifically. Can totally recommend them. And another few MOOCs I want to point out specifically. There is one, Mathematics for Machine Learning, on Coursera that is really good specifically to brush up on the math foundations you need for machine learning and AI. And there is another one that is called Data Mining with Weka. Weka is a data mining software or data analysis software, open source, freely available, developed by a team at the University of Waikato here in New Zealand. And it's an excellent software to play with data sets and find patterns and look into data and understand the meaning of the data you're dealing with. And they've produced a bunch of MOOCs around their software, which is really nice. On a more interactive level, there is a tool called GeoGebra, and we come to that. They have a really nice community. There's Wolfram Alpha. They have a free and a paid version where you can give the Wolfram engine a mathematical problem, and it calculates it for you. And if you're on the pay tier, you get step-by-step solutions. It's not really expensive and it's not perfect, but it can help you if you have no one to cross-check and to correct your knowledge or your learning process. So you can punch a task into Wolfram Alpha, and it gives you step-by-step instructions, and you can get something from that in a way that you would, get a hint of maybe why a certain problem isn't working, or why you're stuck at a certain position in your progress. And from a reading point of view, there is a set of online tutorials from a person called Paul Dawkins, intermediate to advanced level, I would say, mainly looking at like early university kind of level. Really good stuff for this kind of knowledge you want to gain. And then there are a few good books. One of them is from Jeremy Kahn, A Programmer's Introduction to Mathematics. That is nice because it tries to teach math from a programming point of view. And that is an interesting, change to the typical way how math's taught. And the other one is Elements of Mathematics from Euclid to Gödel. And that gives you kind of a not extremely formal, but, like still useful and still entertaining way of going through a lot of the mathematical foundation that you want to brush up onto. And then there's apps and software. I mentioned GeoGebra again. GeoGebra is like a geometry tool, and that's what I used for these vector diagrams, for example, and the vector rotations. And they have a very active community, and the software allows you to build interactive playgrounds where people can do stuff with it as well. There's Octave, which is basically a software to run massive numerical solutions. Then there is TeX and LaTeX, which is a mathematical typesetting solution because no one uses Word or anything like that for math. It's basically a programming language to write mathematics, and it's really cool. It's really versatile, and a lot of people use it for different things, like for articles or for writing a book even. Or I have a friend who actually manages their CV in TeX and LaTeX. And then there's stuff like R, which is a math and stats specific language environment. If you do lots of statistics, you would, have had some exposure to that most likely. And with that, we are at the end. I hope, and I really look forward to more people getting back into mathematics. And I hope you enjoyed that, and you enjoy, having a bit of inspiration of what you can do and why mathematics can be and will be useful for your day-to-day life as a developer as well, and even if you do something that is very independent from any mathematical concept, it can be a really nice and fun thing to do and a fun thing to play with. Thanks a lot for attending this talk, and I'll have a quick look into the Slack channel if there are any questions that popped up.
Yeah, thank you, Kai. Right now I can see one question. All right, let me so do you happen to have any reading/resource recommendations for kids who already love math to introduce them to programming from a math perspective?
That's tricky. It depends on the age of the kid, obviously, as well. I would say your best bet is probably there are like a few specific kid-specific programming environments, and I forgot the name of what they are. I've got one on my iPad somewhere, but I would look into these kind of things. I'll post the name of something I can think of in the Slack channel. But it's kind of hard, right? You find that a lot of kids who are into math and into science in general, to get them into programming, stuff like, I don't know, robotic things could be interesting in general, I think, or, like moving a turtle around the screen and stuff. Yeah, Scratch. Someone in Slack was just saying Scratch. That's exactly the programming language I was referring to. Okay, so Fuda is saying Scratch is too basic. Yeah, I don't know. That's kind of tricky. I think like a good introduction to programming from a language point of view in general is Python, from my point of view, because it's simple, it's easy, it's pretty much like scriptable, and you can just write a big script from top to bottom without having to deal with too much programming structure. And Python has a lot of interesting mathematical functions as well. There are Jupyter notebooks, there's NumPy, and there are a bunch of really good libraries. So I would, if it's for young college age kids, I would maybe look into that then as an option if Scratch is too basic.
Great. All right. Right now someone is typing, so we're gonna hang on a little bit.
Sure.
But otherwise, the Slack channel is available, and the day just started for Kai, so he will be around. We may be sleeping,
yep,
because time zones. So I think they are still typing. Several people are typing now. So I'm not going to just hold the air until they're done typing. But we're just going to take this conversation off the Slack. But thank you so much. And I'm going to hand it over to John for the closing remarks.
Cool.
All right, then.
Thank you.
Thank you.